I am Martine Rutte, Associate Professor Water Management and Climate Adaptation at the TU Delft. This week we will discuss river engineering and specifically the building blocks that were introduced in the Netherlands after the floods in the 1990s to increase water safety and reduce flood risk while also increasing landscape values. This week we will focus on the technical and engineering aspects. The landscape design aspects will be discussed in week 4. Within the Room for the River program, at the beginning of this century, several building blocks were introduced to increase the capacity of a river system, and these building blocks are depicted in this image. These interventions were directed at reducing the water levels in the rivers in the Netherlands, including the Waal, the case study of this week, and reducing the water levels was basically done by increasing the discharge and the storage capacity of the river systems. Note that this set of building blocks was designed for the heavily engineered, canalized river systems in the Netherlands. For other river systems, this set may look very different, and we will get back to that at the end of this lecture. Let's look first at a few equations that help understand the effectiveness of these measures. The first equation states that the discharge capacity equals the flow velocity times the wet surface area. So basically, if the cross-section is increased and the flow velocity stays the same, the discharge capacity increases and the water course can transport more water. From this equation, you may get the impression that this is linear, but this is not always the case, as we will discuss later. Most building blocks were directed at increasing the wet surface area, as the name Room for the River already implies. An example is a lowering of groins. These structures were intended to prevent the natural meandering of the rivers discussed in week 1. A continuous changing water course is difficult to navigate, and in addition these groins help deepen the main channel, also beneficial for navigation, and protect the embankments from creeping ice, debris and wave attacks. By lowering the groins, it was aimed for the groins to keep these functions but allow for more water discharge during high flows. The discussion on design of river training such as groins still continues. For example, the deepening or erosion of the main channel is going so fast that it's threatening infrastructure, ecology and navigation. Groins parallel instead of perpendicular to the riverbanks are under investigation as an alternative, but also more drastic changes to river management are being discussed. You can imagine how deepening of the riverbeds, dike relocation, high water channels, lowering of floodplains, etc. would increase the wet cross-sectional area and could thereby increase the discharge capacity. The second component in the discharge equation is flow velocity. What does this flow velocity depend on? A simple equation to calculate flow velocity in water courses was developed by the Irish engineer Robert Manning in the 19th century. Basically, the flow velocity depends on the slope. The steeper the water course, the faster the water flows. The roughness, for example, bed vegetation slows down the flow. And last, the hydraulic radius. The hydraulic radius is basically a measure for how close a water course is to a smooth, half-round pipe, the most efficient shape to convey water. For the wide rivers considered in this MOOC, you may take river depth as a proxy for hydraulic radius. Of course, the flow velocity pattern in a river is much more complex, with, for example, stagnant zones in inner bends and just downstream of groins, and flow acceleration in other zones. These flow patterns are very important for water and sediment transport and as such crucial to understand in river engineering. Yet this equation is useful for first-order calculations and understanding. For example, flow velocities over vegetated, rough floodplains may be low if not maintained. In addition, floodplains provide additional storage capacity in the river system. Detention reservoirs do this as well. Storage capacity can help to dampen the flood wave and let it safely pass. Yet how effective are retention areas for extreme discharge events? For the typical flood waves in rivers such as the Rhine River, a lot of storage is needed. Let's have a look at this hypothetical example with a flood wave of 80,000 cubic meters a second in a river with a capacity of 16,000 cubic meters a second with a duration of 1 day. These figures are roughly based on the Rhine River. We can roughly estimate the storage needed by calculating the surface area of the hydrograph above the capacity line. If we approximate this with a rectangle of 1000 cubic meters a second high and 24 hours times 60 minutes times 60 seconds wide, we arrive at a volume of about 86 million meter cube. This equals in the order of 6,000 soccer fields with a flood depth of 2 meters. So water retention requires a lot of space, but can still be desired, especially as droughts are also becoming more frequent in the Rhine basins and many other parts of the world. The last measure we will have a detailed look at is the removal of obstacles. This helps to increase wet surface area and flow velocity locally, and thereby the discharge capacity. Yet its effect can propagate upstream. This is due what is called a backwater curve. Basically, structures like bridges act as bottlenecks in a river system, and this results in higher water levels upstream of the structure. This backwater effect may be aggravated by, for example, debris that is trapped at bridges and other obstacles. The set of building blocks developed in the Room for the River project provides solutions for the heavy engineered water system in the Netherlands. In other river systems, the solution space may look different and may be larger or smaller. What building blocks are possible when using natural processes such as sediment transport, meandering, or biological processes? What would the set look like if you take more perspectives than floods into account, for example, droughts, water quality? Can you develop a set of building blocks to add to your river biography?